So today we're going to be finishing off benefits of miniaturization, where we talk about that micro gas chromatograph. We'll finish that up. And then we'll start talking about processing. And this is the place where we're going to go very, very quickly. And so if you don't have a background in processing, you're going to think I'm going way too fast. And I probably am if you don't have a background. But again, you can pick up on this stuff fairly quickly by just reading the Jaeger textbook that is part of the textbooks that came out with this class. It's not a required textbook, but it's a textbook that you can look at if you're having problems with processing. I guess before I talk about any of that, let me just talk about an announcement first. That's in homework number 1, problem number 2. That problem is kind of ill-formed, okay? It's still very doable, and if you just follow its instructions, you can do the problem, but it is ill-formed because it's not, that's not the way you would really solve that problem. Okay, so let me just say a few things about it. So problem number 2, we have an accelerometer. And it's an analog devices type accelerometer, so it's got a proof mass that looks like this. This was in your lecture notes and in the module as well. And so that proof mass is held up by these springs. And so the problem statement says that the springs are compliant. Well, they are. They're compliant in this direction. But they're not compliant in that direction. Okay, and so if you want to determine whether this proof mass is actually buckling, which is part of that problem, you have to include the springs too. Okay, but there's where the problem is ill-formed. The problem doesn't give you any information about the springs and that sort. So it's ill-formed. Okay, and maybe luckily so, because you're not prepared to be able to do a problem where you can handle the springs and the proof mass. Okay, so for this problem, just do the following. Okay, don't assume the actual accelerometer like this when you're going to determine buckling of the structure. Just assume that you have that big plate structure where you're given the dimensions, and assume that it's anchored at both its ends. Okay, this is a situation where it can buckle, where the equation given for buckling can be used. Okay, and all of the stuff you'll do in terms of what the yield of this thing is and all that stuff that question asks, they're valid questions, but not for this accelerometer. They're valid sort of for this here. Okay, so all the questions are still valid. They're still the type of exercise you would need to do in order to figure out what the yield of an accelerometer might be in a certain fabrication process, but it's just, the problem is just not entirely correct. And so if you notice that, I just wanted to say something about that during this lecture. Okay? Any questions about this? Yes?
So in practice, the presence of the beams has...
Well, actually, no. It may increase buckling, but the buckling will be in the beams instead of the proof mass. Okay, so you now have to, right, because it's now a longer structure, which means that the difference in thermal expansion between the substrate and the structure could be bigger in this case. These are also thinner beams here, so you may have a worse problem. But anyway, the reason why it's not that important to have this problem absolutely correct now is because we're going to do this much later in the semester, right? This was meant to be a problem where you just play around with things. That's all homework 1 really is anyway. It's a very simple homework. It's meant to be very easy, and it's meant to be very easy so it doesn't take much of your time, so that if you do have to review processing, you have time to do it. Okay, so you're given lots of time to review processing. All right, but before we go into processing, so that's my only announcement. Okay, I guess one more announcement here. Someone asked if the discussion time could be moved. Now, in the past, that's been impossible for this class, and I'm kind of assuming that it's impossible again for this class. So let me just ask this question. How many of you would be conducive, amenable to moving the discussion section from its present time now? I could choose almost any time, like Friday afternoon. Is that a possibility? Do you have a class during that time? Do you, right? See, so I don't remember who asked the question, but this is what happens basically. I can go through every hour of the week, and there's going to be someone who doesn't want to do it. So the easiest thing to do is you have the discussion section where it is right now. The problem is there's another class that overlaps the discussion section. Is there anyone else in that boat, by the way? How many people are in that boat that have a class and can't go to discussion? You could tell me later on. So there's one person, right? But for one person, I can't do it, right? And I think, the discussions, how important are they? They might end up being important to some degree because you'll learn Coventor wear and some of those things there. So you have to make a decision, right? Because it's almost impossible to move the discussion section with a class this big and everyone in that discussion section, okay? So I just wanted to mention that. I just wanted to poll how many people have a problem with it. Because if it's 5 people or 6 people, then maybe we should do something about it, okay? And so if you don't want to identify yourself here, you could tell me after class whether you have a problem with it too, and I'll take account of it. Okay, so let's start the actual lecture. So we're going to go back to this thing here. Whoops, we've advanced too far. So we were talking about microgas analyzers. Whoops, what am I doing? Okay, so we went through this. I talked about why it is that you want to have a separation analyzer. It's because what's more important in a sensor is not what it can sense or what its minimum detectable limit is. It's whether it can sense the right thing and not sense other things it's not supposed to detect. That's what a sensor really is, right? Because you think of it, everything is a sensor, right? Say I wanted to sense temperature. Everything senses temperature, right? Even a quartz crystal will sense temperature. Its frequency will shift with temperature. Any analog circuit will sense temperature, right? The currents and the voltages will shift with temperature. Everything senses temperature, right? But the thing is, can it sense temperature and also not sense, say, the hell would it not sense? Humidity or something like that. Can it sense just one thing and not sense the other? That's what a sensor is. It's not something that can detect something. It's something that can detect that something but not detect other things at the same time. Okay, and so we talked about these types of sensors, which are polymers that will change as they absorb gases, and there was lots of money poured into these kinds of sensors. These sensors are used often in a lot of situations, but in those situations where they're used, people don't trust them. Okay, and so I'll give an example, right? So I was at DARPA for a while, so these are some military examples or so, right? But if you have soldiers or so who have sensors that are supposed to detect poisonous gases, right? Well, they had these sensors, right? And these sensors were based on technologies similar to this. They use surface acoustic waves. They put polymers on those sensors. They go out in the field. They all have gas masks and stuff. They're not wearing them because they're uncomfortable. The sensor alarms, right? No one puts their gas mask on, right? Why is that? Because the sensor's done it before, and nothing was there, right? So the problem is false alarms, right? The sensor went off when that gas wasn't present, the horrible gas wasn't present, but some other gas that was very similar to that horrible gas made that sensor say, yes, that's what it was. And so in the end, what did they do? They trusted birds more than the sensors, right? If the birds died, put the mask on, right? So that was the problem here. That's why a lot of effort was put into solving this sensor problem, that these weren't selective enough, right? And this was one of the best solutions to that here, to actually separate out the analytes, then sense them one at a time. And we talked about the problem with this, that they're too big, and so this sort of shows the problem. This is a small-sized one. This is one you can actually carry in a suitcase, walking around. But what was really needed is something that's in a much smaller size, so 1 to 2 centimeters. You can see the amount of improvement that was asked for at the beginning of this, which was a DARPA program, right? And the reaction to this, basically from most proposers, were, oh boy, that's impossible, that's stupid. You can't get 20,000 times better. You can't get 1,000 times. You just can't do this, right? That's what people were saying in the beginning. And so there's where I'll remind you, the experts are not the experts. Okay? Don't listen to the experts, because they're the ones usually who are going to tell you it's impossible. You should listen to the experts, but not all the time, right? Take it with a grain of salt, whatever they say. Okay? Because that's what was happening here. A lot of people were saying, look, I spent 20 years doing this. You're not going to do any better than this after my 20 years. Right? But all it takes is a different idea. You know, an understanding of something slightly different that takes you from here to here. Okay, and so this is what this program was going after. So how does it do it? Well, let's talk about what a separation analyzer is. Okay, so it's a gas analyzer, so the input is a gas. And so this could be your gas. And usually what's your gas, right? What's air? Is air just oxygen? Is it pure oxygen? Absolutely not, right? You've got all sorts of things. Nitrogen, all sorts, who knows, right? There could be ammonia, all sorts of things that you may not want to smell or so, right? But it's all in the air, you know, cleaning agents, that sort of thing. And so usually you're sensing not just one or two things. You're sensing 30 different things. Okay, and so how does this thing sense that? So this goes about first pre-concentrating all of this gas. Okay, so it collects the gas over a certain amount of time, and that's called pre-concentration, right? Because the gas is too, you know, it's not a strong enough concentration where it is, right? And so it goes in and it absorbs onto maybe a polymer in this case, right? And so it's collecting all that gas. And then after a certain amount of time of collection, you then expose that gas somehow. And a lot of times you're just putting heat in, and that heat just removes all the gas from the polymer, and it does it almost immediately. And so because of that, you had gas that was streaming in like this. Suddenly what comes out of here is just a plug of that gas. It's very compressed into a very small plug. And that's good, because what you want to do is separate out the gas. And it's tough to separate something that's a blob like this, right? But if it's very compressed, then it separates out into lines when things go at different velocities down the separator. And so here's a separator. So it's a tortuous path for the gas to go down. The gas is interacting with the walls as it does this, and different gases interact with the walls differently, so the velocity at which a gas gets from the input to the output is different. And so ideally what you have are different slices, plugs of gas coming out, one at a time, if this column is long enough, and now your detector out here can detect them one at a time. It's no longer having to detect a mixture, which is something that sensors can't do. Detectors have a very difficult time sensing mixtures. Okay? And this solves that problem by removing the need to sense a mixture. Okay? It's just like communications. In communications, you have a filter that filters out most of those signals you're trying to pick up with your phone. Right? This is doing the same thing. All right? Now, the problem is, and this is how the macroscopic ones work too, but the problem with the macroscopic ones is things are slow, right? You looked at that chart back there. They were slow. You couldn't detect very well, and it took too much power. Okay, so here's where miniaturization solves all of those problems. So the pre-concentrator, I just described you how often they implement these things. You absorb on a polymer, then you shove heat into the thing, right? And then the gas comes out almost immediately when you shove that heat in. Well, you're shoving heat in, that's power. Right? What did we learn from our atomic clock discussion? You make it smaller, you get rid of the power. Okay? The other thing we learned from the atomic clock thing is that thermal time constants are much quicker. So if you had a large thing and you put a lot of power in, it's going to take, you know, a few seconds for that thing to ramp up in temperature, which means that the gas is going to come out of that polymer in a few seconds. You're going to have a plug that's a few seconds long. Okay? Well, that's kind of thin compared to a minute, right? But if you want this thing to do its whole analysis in 4 seconds, a few seconds long is too long. Okay? There's where the MEMS comes in. There's where miniaturization solves, whoops, why did it go that way? There's where miniaturization solves a lot of problems. So this is an example of a MEMS-based pre-concentrator. It's just a membrane here. It has several pieces of polymer here. And what's happening, these pieces of polymer are so small, it takes very little energy to heat them up to a very hot temperature. And they're also very fast. So what they do is they push out, see, this will push out once, then this will time itself so that when the particles reach there, it pushes out, right? And then so on and so forth. And what you end up doing is you end up concentrating the input sample by more than 10,000 times. So it becomes concentrated by more than 10,000 times its original concentration in the air. Okay, what does that do? That means that your sensitivity at the end for your detector can be 10,000 times less. Right? It doesn't have to work nearly as hard anymore because you've concentrated that sample. Not only that, because it's pushing this stuff out now in time constants of milliseconds, right? You're talking 10 millisecond time constant. Your plugs are now about 10 to 20 milliseconds long. Okay, compare that to a few seconds, 10 to 20 milliseconds. Okay, almost 1,000 times thinner plugs. That means you really have a slice of stuff. And that means it's going to take much less distance to separate them out. Okay, and so then you had your separator. And it turns out that with your separator, the smaller you make the separator, the smaller you make the columns, the distance between the walls of the column, the better the separation becomes. And it becomes better because, think of the plug. As the plug is moving along, what happens as something moves along? It never stays exactly the way it looks, right? It always moves along, and then it gets fatter and fatter and fatter, right? Because things don't diffuse at exactly the same rate, right? There's some statistics involved by how fast each of those particles go. Okay? And some of those statistics you can help out by making everything smaller. Okay? There's lower power too, because oftentimes the separator has to be heated too. Okay? But let's talk about this better separation. So this is where smaller is better again. Okay, so how do these things separate? Well, I talked about the fact that you've got the gases, right? What they do is they adhere to the walls, and then they're really moving by jumping from one wall point to the other. Okay, so for example, these gas particles can move like this. Okay, so they're moving from one point to the other. If they did that, that would be great, because you see the original width of that plug is still the same here. But what really happens is some of these go out further than others, right? And so some of them go much further than others, and what happens is you now get a wider plug. So as this thing is going down, that plug is getting wider and wider. Okay, that's a bad thing, because that means if your peak broadens, you have to separate them by more distance in order to resolve them. Okay? So what you'd like is some way to separate them without broadening the peak, and that's where making this channel a lot smaller helps. Okay, so if the channel's a lot smaller, these molecules have nowhere to go. Right? They don't have the option of going very far away and ending up very far here. They can only go a certain distance there, or they can go across to the other side. But as they move across, this plug doesn't get much fatter. And that's happening because we shrunk the size of this thing. Okay, so this peak goes across. It stays thin. You need less separation to resolve this. That means the column could be much shorter. Okay, and if the column is much shorter, that means the separation can happen much faster. Okay, and so that's what the program was going after. You know, column width goes down. It's really a surface to volume ratio going up. That's what's really helping you. We've seen that surface to volume ratio thing before. The peak spreading goes down, and so the distance required to separate, the length of this column becomes shorter, and the analysis becomes faster. That's how the 4 seconds is done. Okay, and you're going from 15 minutes, right? Some of them 2 minutes or so, to 4 seconds, right? Just because you're shrinking this thing down. Okay, that's the good, but what's the bad with doing this? Where do you run into a problem when you're trying to shrink this down and get better resolution in your separation? Yeah, the gas volume is smaller, but that's okay because we pre-concentrated. Yeah, okay, so you could say that that's an issue, right? When you make things smaller, you're working with smaller amounts of gas. Okay, so that was an issue, but we solved that by pre-concentrating, by a much larger number of times gain factor than you can on the macroscopic scale. Okay? The other problem is that when you make a column that thin, now the pressure drop across this required to move things along is much larger. Okay? So your pump has to be able to maintain a larger pressure drop. And you have to be able to solve that problem, which is not an easy problem to solve. Okay? So that's where, you know, people were running into issues in implementing this thing. You know, can you get the right pressure drop over a small enough column? But, you know, they were able to do quite a bit. This is work from Sandia, actually. They made a microgas chromatograph column here. You could see separation of several different analytes here, all in less than 4 seconds there. Okay, so this stuff really does work. Going to the small size is able to allow us to do this kind of thing. And now if each of these are detected one at a time, you have a much smaller false alarm rate to the point where you can trust what your sensor is telling you. And so let's talk about that detector. Okay, so shrinking the detector also helps you out in a big way, because a lot of these detectors, when they're detecting gas, they're based on detecting mass. Okay, so they're based on a percent change in mass on the actual detector. So you could have a detector that looks like this. It's a resonant beam. So a lot of the best detectors are actually resonators, a resonant beam. And when you get a gas molecule or several gas molecules impinging on that beam, absorbing to the surface, that changes the resonance frequency. You detect that shift in frequency as the presence of that particle. And it turns out we can detect shifts in frequency much better than we can detect changes in voltage levels. Okay, so that's why resonant sensors are some of the best around. But they also get much better as you shrink their sizes. Okay, because think of it, you're shrinking a beam down. So you have a beam resonator like this. You shrink it down to maybe a nanoscale like this. Now suddenly the beam is so small, its mass is tiny, its volume is shrunk enormously, while its surfaces, the surface-to-volume ratio went up. So now the surfaces that the gases can interact with have gotten bigger. Effectively, they've gotten bigger. The mass of the thing has gotten smaller. So in the end, now the delta M over M, the percent change in mass, is much bigger when you make things tiny. And so it is nanoscale vibrating resonators like this one demonstrated by Michael Rukas at Caltech that have the record performances in how small of a mass change you can actually detect. So this is detecting about 100 zeptograms here of mass change. What's a zeptogram, right? So that's the questions that come in, right? Suddenly we're able, with this going to nanoscale, shrinking things down, now we're dealing with words we don't really know that well, right? Zepto's 10 to the minus 21. Okay, so we're detecting extremely small. And you see, it's not, you're not going to come, we're getting closer to be able to detect single atoms with this type of technique here. Okay, and this is all a resonant sensor. It's become much better just because you've shrunk it down enormously here. Okay, now this is also, you know, this is just the resonator. The gold atoms are just being thrown at this thing. Okay, and so it's not really a sensor yet. You got to put a polymer on this that detects a certain gas, and maybe you don't if you have this gas analyzer, right? If it's separated, now you may not need that much selectivity in your sensor, and maybe this could work here. Okay, but this was one of the sensors being pursued here. And so in the end, right, just to sum everything up, you know, this program went from this here, which is a tabletop gas chromatograph from Agilent. You can see the sizes of that. And, you know, just, you know, recognizing that gas chromatography mass spectrometers are the gold standard. Gold standard, what does that mean? That means that you can trust it pretty much. Right? These are the best you can get today. Right? These are better than spectroscopy, better than any of this. Spectroscopy has problems in trying to analyze a mixture because of nonlinearities. Right? If you have many gases together, they interact with each other that create then peaks that aren't supposed to be there. It's just like nonlinear electrical signals coming together, going through a third-order nonlinearity and creating an IM3 distortion. Right? When you have things together and they mix, and you have nonlinearities in the system, you create things that weren't there. Okay? And so that's the problem with spectroscopy. But this solves a lot of problems because it's not trying, you're in the end not trying to handle the whole mixture. You're separating it out first and then handling each piece one at a time. So in the end, interestingly enough, what am I doing here? Why does this not? Okay. Interestingly enough, some of the teams did make these goals here. Okay? Not in a practical implementation. Okay, but, and so it takes a lot more money and effort to put it into a practical implementation, a practical product, but these types of goals were made. Okay, so where a lot of people were saying impossible, here it is. Right? It's doable. And in the end, right, I've given you three main examples of how miniaturizing things can improve performance. There's an infinite number of things out there. Right? And so it's very easy for me to come up with a project for someone to do if I needed to. Right? Because all I have to do is look around and say, okay, what's out there? What needs to be shrunk? And what kind of gains can we get by shrinking this? Okay? And that's pretty much how people create MEMS projects. They look at something that exists. They say, okay, let's make this smaller. Oh my gosh, we really need to do this. Okay? So we can even go back to this, right? The accelerometer, right? Which is something that I talked about before. This seems to defy that rule, right? You make the mass smaller, and the accelerometer gets worse. Right? There's no way around that math. That's true. That's just what happens in this. So there's cons, there's pros. But I think I mentioned this before. The pro to this is that this accelerometer now can survive very high g-forces and can actually operate under much higher g-forces than macroscopic accelerometers. Okay, so they've taken accelerometers like this, which is actually in your automobile, right, and shot them in missiles. Missiles explode, accelerometer's still there, right? So the size and that ability, right, you know, when you get smaller, the inertial forces are smaller, and so that's part of why these things can survive. Okay, so there's always a pro, there's always a con. But as long as you can get past the con, and they do it here by integrating with electronics to allow themselves to detect the very small motions of this thing, then it becomes a win-win in technology. So I guess just to end this benefits of scaling thing, you know, I said what MEMS were, and that's really what this was defining here. It's really a scaling technology. So to me, MEMS and nanotechnology, they're all the same thing. Right? MEMS is just the precursor. Nanotechnology. Yeah, I mean, I come from a funding agency, of course. The reason why you have words like MEMS and nanotechnology and stuff is because you can't fund the same thing forever, right? So they've been things, right? So they say MEMS, oh, we've funded MEMS for so long, you know. Let's call it nanotechnology so we could say it's different and so Congress will give us money. That's what happens. That is really what happens. Nano will last for a few more years here, right? And then it's got to be some other name. It's going to be the same stuff, right? More advanced stuff of that. But it's going to be another name and it's going to be another bin, but it's going to be similar types of things, right? People reinvent things and they do a better job of it. And that's what happens. But all these names and stuff, it's all funding, right? Nanotechnology in the end is the chemist's way of maintaining their funding, right? Chemistry people. Maybe I shouldn't have said that. But that's what it is, right? So in the end, right, it doesn't matter whether it's MEMS or nano, it's going to be pico at some point, right? Shrinking makes a lot of sense. Making things smaller in all physical domains makes a lot of sense. And so what's next? Well, even nanonuclear fusion, chip-scale atomic sensors. The sensors are actually already being done now. Okay, so there's all sorts of different things you can think of that have been thought of that people are looking into. And it's just a matter of someone putting funding into these things to help people pursue these. All right, so that's my benefits of scaling thing. And so you have this as a module, of course, online. And you also now have another module online. This is module 3. And I will be lecturing out of module 3, which is on, whoops. Problem here. Okay. Which is on oxidation and film deposition. So here's where we're going into processing. And you saw before, and I guess I'm going to show again, that to make a device the way that we do it at the wafer level, it's just a series of depositions and etching steps, depositions, etching steps. And so what I want to do is go through each of the types of depositions you can do, or growths, and the types of etching, the lithography, and that sort. And I'm going to do that extremely quickly. Okay, because one, I think it's something you can understand more quickly than some of the other concepts we're about to get into. I mean, after this, it's going to get hairy. This course will get hairy very quickly, and not circuit design, it'll be deep physics. So everyone gets fun, right? Circuit designers, the physicists, and that sort. But here we're doing process technology, and to me, this is easy stuff, right? This is stuff you should be able to absorb very quickly. If you cannot, get the Jaeger book. You have plenty of time because your homeworks are Mickey Mouse right now. Okay? Pick up that book and study that stuff if you feel that you're falling behind in this. But I'm going to go extremely fast, and if you think I'm going fast, I know I'm doing it. Okay? All right, so we're going to talk about oxidation first, and then many different types of film deposition, including evaporation, sputtering, chemical vapor deposition, and all the rest that you see here, even atomic layer deposition and electroplating. These are all methods for putting films down on substrates. And before talking about that, let's just talk in general about mechanical fabrication, MEMS-based fabrication. And let's sort of compare it to the way things are done today or yesterday or that sort of thing. So how does one best make a mechanical product? And so you see time and time again there's assembly line production out there, right? People making cars, airplanes, that sort of thing. It's an assembly line. So you got something going through on a conveyor belt, not quite here, but you're picking and placing parts onto this thing. And this turns out to be one of the best ways to manufacture macroscopic things. Okay, but if you're going to try to manufacture a microscopic thing, it becomes more difficult because now you're talking about picking and placing tiny things. And that's a tough thing to do. As we'll see, it's not impossible. There are actually companies that make systems that can pick and place tiny little objects or so. And there are some arguments that that's the best way to make some MEMS products. But it turns out that if you have a low volume product, that's the best way to do it. If you have a high volume product, then you want to do it using what I'm showing here. You want to do it using an integrated circuit type process. Similar process to how they make ICs at the wafer level. And so that's what MEMS did in the beginning. Okay, it borrowed from integrated circuit transistor technology. It just harnessed the batch methods for fabricating thousands of different things on a wafer that we already did with ICs for a long time. And so how did we harness that technology? Well, we talked about surface micromachining already to some extent. And so if I want to create a structure like this that's anchored at these points here, this is all suspended. You can see the shadows underneath this. And this is free to move in that direction there. You're going to be playing around with these quite a bit in this course. This is a classic type of structure that people use. And this is the cross section. The way you do this is, start with your substrate, and you notice we're just putting films down. Okay, films right there, and then we etch the film. So we're etching. Put another film down on this, etch this film. Another film on this, etch that film. Then finally etch out this layer that's temporarily supporting that film there to make a free structure like that. So right there, it's all film deposition. It's etching. In order to etch, you have to do a lithography step that defines what you're etching. And that's basically the process. Okay? And so you're basically putting a lot of steps together. A process flow is like a cooking recipe. Right? Okay, put a little bit of that, put a little bit of that, etch this, heat this up, that sort of thing. It's a recipe is what it is. And so I want to teach you right now how to put down these films. Later on, I'll teach you how to pattern them, how to do lithography, and how to etch them. And I'm going to do that very quickly. But before doing that, that would be the IC way to do things. Okay, here's a method that MEMS actually was using a lot of, that ICs sort of in the end, I don't know which one borrowed from one another, but electroplating is now used quite a bit in ICs to get multi-level metallization. Well, in MEMS, they were doing electroplating quite a bit as well to make structures because it was a good way to make very thick structures. And so for electroplating, same kind of thing. You're depositing some films here. Maybe you'll deposit this film and pattern that. Then you're putting down an aluminum layer. It could have been electroplated or so, but probably was sputter deposited. Then you're etching into that aluminum to create anchors. And now what you're doing is you're electroplating. Okay, so you're actually growing a film in this. And you can grow it so that it's flush with the surface there. That removes a lot of topography. Topography is our enemy, and so we'll talk about that later on too. Then at this point you can put what's called a seed layer here, put down a photoresist, pattern that with lithography to create a mold. And so wherever that photoresist is open, you can electroplate your material in there, right? Then remove the photoresist, remove the seed layer, okay, and then dip this in a solution that removes this gray sacrificial layer. Whoop. And so you end up with this freestanding beam here. Okay, so just another way to make a micromechanics, this time made in a metal. And this is the way people have made RF switches. This is an example of one by Rockwell, when they were Rockwell. They're now Teledyne, actually. I also talked about bulk micromachining. So here's a process that you saw already. So you etch into the silicon, take a glass substrate, etch anchors into this, flip the silicon over, bond it. So here's a bonding technology that was sort of pioneered in the MEMS area. And then dissolve away that substrate to, again, end up with a freestanding device here. So lots of different ways to fab things. But all these different ways to fab things are just based on several modules that we could talk about. Film deposition, etching, lithography. So let's now talk about one of these, which is oxidation. Okay, oxidation is very important for CMOS processes. At least they used to be. Now they're using more atomic layer deposition for the important oxides that they have. They're less important for MEMS, but they're still there. Okay, so I'm going to talk about them, but very quickly. All right, so what is oxidation? This is achieved by heating a silicon wafer to a high temperature in an atmosphere that contains oxygen. It can either contain pure oxygen, which is called dry oxygen, and that would be the reaction, or water vapor, where you're getting your silicon dioxide by reacting water with silicon. There's more molecules in the water vapor, so this is a faster reaction right here, but maybe the quality of the oxide is not as good as dry oxygen. And when you're doing this reaction, right, you're actually reacting with the silicon wafer. So if your starting surface were here, then after you've grown your oxide, your starting surface is going to end up somewhere in the middle there. Some of the oxide grows into the wafer, some of it is extending out of the wafer. Okay, and the percentage is usually 44% into the wafer, 56% out of it. You may see something different than this, and that's because it's different depending on the orientation of the surface of the wafer, okay, which we'll talk about later on. But how does this oxidation happen? So it's kind of important to understand the modeling just to get a qualitative sense of how long something is going to take to grow. Basically, all deposition processes work this way too. So when I talk about this, I'm talking about pretty much all the growth type deposition, LPCVD, that sort of thing. So the first thing that has to happen is that gases that need to react with the surface have to stream in. Okay, so gases are flowing, they have to make it to the surface. Once they make it to the surface, of course, there's a reaction, as long as the temperature is high enough to speed that reaction up fast enough. But then as that film grows, now the gas stream impinges on the top of that film. And now that reactant has to diffuse its way to the surface of the silicon, and then it can react. So after a certain amount of time, this reaction goes more slowly. That means the oxide grows very fast initially, then the growth rate slows down quite a bit. Okay, so that's one of the things we like to do in processing. Processing is a lot about modeling growth rates, determining how fast you can grow a given film based on the physics of what's going on, the physics and chemistry here. And so you can do a lot of modeling for oxidation. And so the models are such that usually you're looking at concentration. So what you're seeing here is along this axis, this is distance from the surface. That's the surface right here. This is already grown oxide right here, so that's silicon dioxide. And then this is the silicon surface deep within this. Okay, and so we'll make an assumption that the concentration of reactants at the surface here is going to be different than the concentration of reactants at the oxide-silicon interface. And that makes sense because the reactants at the silicon dioxide interface, they're reacting, right? So they're going away fairly quickly. They'll have a different concentration. And there's going to be some kind of flux. There's going to be a gradient of oxygen atoms or reactants in the oxide here where they react at the silicon. And there's going to be a flux of these going from the surface to the silicon dioxide interface. Okay, and we can define all of these things as shown here. N naught is at the oxide surface, Ni is at the silicon dioxide interface, J is the reactant flux, defined by diffusion coefficient times the derivative of the concentration divided by, or with respect to distance x into the substrate. And so basically the diffusion coefficient times the gradient of your concentration. In the end, you can define that flux as just d times this straight line gradient here. And the reason why we can say this is that we're assuming that the reactant doesn't accumulate in the oxide, right? If you have no reactants accumulating in the oxide, then you have to have a constant flux through that oxide there. And so that simplifies a lot of our math. We take that constant flux here. We also understand that at the silicon dioxide interface, that's a chemical reaction. From your chemistry, you know that chemical reactions go as some constant times the concentration of the reactants there. And you can then take this information plus the information on the previous slide, equation 1, to write an equation for flux of reactants. This is where I'm going very quickly for you here. You can go back and look at all these things, right? You can then write an equation for the rate of change of oxide layer thickness with time. This is what we're after, so that's dx ox dt. Equate that to the oxidizing flux divided by the number of molecules that oxidizes of the species that are incorporated into a unit volume of oxide. That's different if you're using dry O2 and H2O. Okay, and so you'll have different constants associated with all of this. You have an initial condition, which is just your initial oxide thickness, and you can then just solve the differential equation, and you end up with this. Okay, and so this is an equation where this is the oxide thickness as a function of time, It depends on a constant A, which you can see depends on the diffusion coefficient and the reaction rate, the chemical reaction rate. A constant B, depending on diffusion coefficient and the concentration of reactants that you're throwing at this thing here. This diffusion coefficient, D, has an Arrhenius relationship. And then you have this tau, which is sort of the time, can be interpreted as the time required to grow that initial oxide X sub I, okay, which depends on X sub I, of course, plus these different constants here. Okay? I'm going very quickly through this. This is all in Jaeger. This is all here, too. You can go slowly on this later on if you want. But yeah, I'm going quickly, and I know it. All right, so for shorter times, if you look at these equations, for shorter times, so you make T very small, this thing boils down to something that is proportional to T. Right? The square root function great. The square root function right, boils down to a linear equation, right, when this is a very small number, right? And so you end up having a linear growth initially until that oxide gets thick enough. When that oxide gets thick enough, now those reactants have to diffuse through the oxide to get to the surface to react. And once that occurs, you start getting a square root dependence on time. So that's where we call it a parabolic type of growth. And we call then a linear growth rate constant the constant associated with the linear part of the growth, and the square root B as the parabolic rate constant. Okay? And you have constants for all of these different things. So I guess, yeah, so these are constants for that diffusion coefficient. Okay, so that E1 is the activation energy in the Arrhenius relationship. The C1 is the same as D naught that I had in the previous slide. I guess I'll write in a D naught somewhere else. Maybe I'll write it in right now. So that's the same as D naught from the previous slide. Okay, and this is the same as, I think I called it E sub A. Okay, and that's the same for all these cases. You can see different cases for dry O2, wet O2, or wet oxygen, and then pure water going in. But, you know, that's all great, all those equations. They're great. So I'll tell you, those equations are correct when you're growing oxide thicknesses on the order of 100 nanometers or larger, which is usually what you're doing in MEMS. But when the oxides are very thin, those equations are all wrong. Okay, because different things occur when you're trying, at the initial point, it's not purely linear. Different things actually occur. So if you're trying to grow an oxide that's 1 nanometer thick or something like that, these equations aren't going to work for you. That's something that you have to take 243 for. Okay, so EE243 will discuss that. We won't, though. We won't even care about these equations too much, because in reality, when you get in the lab and you're actually processing, you never use those equations. What you do is use charts. Okay? Why play around with equations if someone's graphed all of them for you? Okay, and so that's what this is. These are oxidation and growth charts. You find this in every lab, microlab. This is oxide thickness versus oxidation time on log plots here. And so what you do is, and they're for different types of silicon. So that's 100, this is 111 here. And you know, you find what kind of oxidation you're doing. If you're doing a wet oxidation with water present, you look for your temperature, and you can figure out the amount of time required to get a certain amount of thickness. Okay, very simple stuff. Not actually completely simple, though, because how do you do this if you already have some initial oxide on the surface? Okay, so this is a problem. Here's an example here. Say we have 100 silicon, and say that this silicon, you got this silicon, but someone had already put 100 nanometers of oxide on this. Okay, maybe they grew the oxide, maybe they deposited the oxide. You don't know how they put the oxide down. You don't know what temperature. You don't know if it was wet O2 or dry O2. Okay, and now what you want to do is you want to grow, or you want to do more wet oxidation. You know you're going to do it at 1,000 degrees C, but you want to achieve an oxide thickness of 230 nanometers by the end of all of this. Okay, so how are you going to figure out how much time is required to get that 230 nanometers in the end? Okay, so you can go back to those equations, and that's easy enough, right? Just plug in for X sub I 100 nanometers, and you can use those equations. But you may be wasting your time because it's a little bit easier to do it. It's a little bit easier to do it graphically here. Okay, And I wonder if this is big enough for you to see as I do it graphically, but I'm going to do it graphically for you right now. So what's happening? We're starting with 100 nanometers of oxide. Okay? And so I have to look for 100 nanometers here. This is in microns. Okay, so that's the 0.1 mark right there. Right, so at 0.1 is my 100 nanometers. So I'm going to draw a line across here. Is that a straight line or is it? Okay, so I'm going to draw a line across there at 0.1 nanometers. Let me paint that line red. Okay, and so now I'm going to look for my process. So, yeah, so we don't know how that oxide was grown, and we don't care. It doesn't matter how it was grown, right? It's oxide. It's going to prevent diffusion of our reactants to the substrate, and that's all it's going to do. It doesn't matter how it was grown. Okay, so it's going to prevent that diffusion. And so if I want to grow at 1,000 degrees using wet oxidation, then I need to find the amount of initial time required to get that 100 nanometers of oxide, and I can do that by just drawing a line here, right at that point there. Okay, and so the amount of time required to grow that initial 0.1 microns or 100 nanometers of oxide is this amount of time, which is about 0.18 hours. .18 hours of time was required to get that amount of oxide. That is what tau is in that equation that I showed you before. Okay? Do we care that that's how much time it took? I don't even care. Right? It doesn't matter to me because I'm not looking for that time. I'm looking for how much time I need to oxidize to finally get to 230 nanometers. Okay, so in order to do that, I'm going to find 230 nanometers here and draw a line across there. So that's about 230 nanometers right there. Let me paint that blue. Okay, and now I'm going to find that same curve, 100 degrees C, wet oxidation, and I'm going to take a line and have it intersect that curve. You can see I've done this before because I have little slashes there. All right, but now this is the amount of time that I have to actually oxidize to get my 230 nanometers. Not from this point to there, but this. Okay? That now is the time needed. To get 230 nanometers. Okay, and if you look at this, this is going to be about 20 minutes. So what you would do is just look at this chart. You know you have 100 nanometers to start. You look at this chart. You look for 230 nanometers. You stay on the 100 or 1,000 degrees C wet oxidation curve, and you figure out very quickly, I need 20 minutes in order to get 230 nanometers. And then you stick it in the furnace, and you're done. Right? No calculations, nothing. Okay, so that's how these charts are used, and that's what people do. No one calculates anything anymore. Did you have a question?
Yeah, this seems kind of approximate, though, because you put it in for 20 minutes.
Yeah, that's true. But everything is approximate in the end. So for example, when you're working in the lab and you want to have, first of all, my wanting 230 nanometers may not be that reasonable. Because even across the wafer, maybe some parts will be 230 nanometers, but others may not. Right? So there's variance in all of that. So it makes no sense to be too accurate about it. You can chug into the equation and get a very accurate answer, but in the end you'll do no better than this because conditions change. How many wafers do you have in the tube? All of those things. So when you're designing a process, thicknesses you can get fairly close to what they need to be, but you can never say that you're exactly on. Okay, so a lot of times this is good enough. Who knows? Maybe the equation can be a little bit better, and so if you really need to be accurate, I would use the equation, right? But usually, if you have something that requires that kind of accuracy, probably not a good product anyway. Okay, so this is how basically people do it up there, and I just wanted to show you this just to make sure you can do that for this class. All right, so keep going with oxidation at our extremely fast pace. So in summary, factors affecting oxidation are things like time of oxidation, how long do you do it, the temperature that you do it at, the partial pressure of the oxidizing species. It's also dependent on reactant type. Okay, so we're using dry O2 or water vapor, where water vapor is faster, since water has a higher solubility in silicon dioxide than O2. The crystal orientation matters. 111 is faster because when we talk about 111, you'll see that a 111 surface has more bonds available at the silicon surface. So you get a faster reaction there. We don't use 111 wafers for CMOS or circuits because 100 has fewer interface traps. Okay, so even though 111 is the faster oxidation, we use 100, not because of oxidation, but because you could do it with very few traps in the oxide. Okay, we don't even care about this anymore because nowadays we're not using silicon dioxide as our gate oxides. We're using atomic layer deposited oxides with much higher dielectric constants. Impurity doping. So phosphorus, it'll increase the linear rate constant. That means it'll make the reaction a lot faster, but it has no effect on the parabolic rate constant. So faster initial growth, and then, so initially it's surface reaction rate limited. Okay? Boron has no effect on the linear rate constant, but it does increase the parabolic rate constant because when it gets into the oxide, the oxygen can diffuse faster through the oxide. So that's it for oxidation. I did that very quickly. Let's now move on to thin film deposition. And so here we're talking about many different ways to deposit a film. So there's evaporation, there's sputter deposition, chemical vapor deposition, plasma-enhanced chemical vapor deposition, epitaxy, electroplating, atomic layer deposition, lots of different ways to do it. And what you'll be having to decide later on is how you're going to do it. Okay, for a given MEMS process, which is the right one to use. So that's what my main goal is here, to try to give you some information on what is the right process to use so you can make an informed decision when you're designing a MEMS process later on. Okay, first let's talk about evaporation. So in evaporation, what you're doing, usually you're depositing a metal by evaporation. And so what you're doing is you're heating up that metal to the point of vaporization. You are just heating the heck out of it. Okay, to the point where it evaporates, and it evaporates onto the surface of a wafer, so it coats that wafer surface. You do it under vacuum for better control of film composition because you don't want other foreign objects to get into that film. You also may do it in vacuum because if you heat a metal up, right, you can grow an oxide too. So you really don't want oxygen around and that sort of thing during this process. You want it in a nice vacuum. And so this is a picture of the system here. So you may have a tungsten filament, just like like a light bulb filament or so. You're going to put voltage across that. You're going to joule heat that. That's going to heat up fairly quickly. It's going to melt the tungsten, and the tungsten is going to evaporate onto the wafer below it. You have a vacuum pump that pumps this to very low pressures. You do this in very good vacuum here because you want the mean free path of the aluminum or whatever you're actually evaporating onto this to be very long. Okay, so that means they don't bump into anything as they're going towards the wafer. Okay, so mean free path is given by this expression. So lambda is the mean free path. It's a distance in meters. KT, Boltzmann constant temperature, divided by 2 pi pressure, P, divided by the diameter of the gas molecule. Okay, so yeah, it's a gas, aluminum, or whatever the metal it is. And so pressure becomes important, right? You want that pressure to be very small. And so, if you put your pressure at 0.75 microtorr, where these things usually are, they get down to the 10 to the minus 7 torr, 10 to the minus 6 torr level, you're looking at a mean free path that's 60 meters. Okay, so the chances that for a 4 angstrom particle, so the chances that a 4 angstrom particle is going to hit something going from your filament to your wafer is very small. Okay, so you can think of this as a point source. Right? You have a point, and you got atoms then coming out in all different directions from that source onto your wafer. And so it's a good way to deposit metal over a wafer. It has some problems, though, in that, for example, if you have a large enough wafer, it's close enough to the source, and usually you're not depositing on just a flat wafer. You're depositing on a wafer that has had some holes cut in it. Because usually for metals, you're trying to make contact to a layer below. And so what you do is you have a point source here. You can see that this point source, you can draw lines to here. You're going to cover this, but you're not going to cover this. Okay, so this is the problem with evaporation, and the reason why people don't use it for a lot of CMOS anymore. It's because you may get things like this, and this is a disaster in CMOS. It's a disaster in most processes because what this means is maybe you don't make contact between this and that, okay, where you were supposed to make contact. These are two metals. You're supposed to make electrical contact, but in this case, you're not making contact. Okay, so how do you solve this problem? Well, there are ways to solve this problem by moving the wafer with respect to the source, and that's what most evaporators do. The evaporator in our microlab here, nanolab here, does exactly that, so you get better conformal coverage over all of these features. And so when I talk about coverage like this, in a way I'm talking about conformability. So the word conformal means that when you're depositing a film, it's covering everything. All the crevices, all the corners, and that it covers everything. This is an example of non-conformal. This is an example of more conformal here. But this is conformal probably because you're rotating the wafer during evaporation. You're moving it around during evaporation. It's also more conformal in this case because another strategy you can use is to etch your sidewalls if you're making a hole such that they aren't straight. Etch them so they have an angle like this. And if you have angled sidewalls like that, it's easier for a film to come down and conform to that. So in essence, a lot of oxide etching recipes that they have for semiconductor equipment, they actually are designed not to get straight sidewalls, but to get angled sidewalls. Because usually the next step in after oxidation is cutting vias so that you can make contact from one layer to another, electrical contact. Okay, so oftentimes these aren't good enough, though. So what's a better way to put down a film? I don't know better, but another way to put down a film, that's sputter deposition. Okay, so this is where you're now depositing at a higher pressure. Okay, so now the pressures are in the order of 750 millitorr. And what's actually happening is you're taking the wafer, putting it under a target. The target is made of the material that you want to coat the wafer with. And you now have lots of different materials you could do this with now. It could be aluminum, other metals. It could also be silicon dioxide, silicon nitride, all sorts of things can be sputtered onto a wafer. Because what is sputtering? You're basically just firing up a plasma, which is a cloud of ions. So maybe argon ions here. And then you're directing these ions right on the target. And so what they do is they physically bump off atoms from the target. And these atoms then make their way down to the wafer. But because the pressure is higher in this case, the mean free path of these atoms is small enough that it doesn't go straight down to the wafer. It takes a tortuous path. Okay, which means it comes down on the wafer at random angles, which means you're not going to get this shadowing effect if you're doing a sputter deposition. Okay? And so I guess I have the procedure for doing this. I just went through that. You fire up a plasma, bombard the target, it dislodges atoms. Atoms make their way, in a tortuous, in a random fashion. At this pressure, which is 750 millitorr, lambda's on the order of 60 microns. So they're bound to hit something as they get to the wafer. The result is better step coverage, what we wanted. The other results, though, are what we wanted to avoid with evaporation, right? So in this case, right, it's part of the reason why you put evaporation at such low temperatures. You don't want other substances in your film. Well, you do get other substances in your film this time. Argon can get in there. That's not so bad. It's an inert gas, but you may not like that. Yes?
What is the difference between uniformity versus...
Uniform. Oh, did I talk about uniformity yet?
No, it's just on the slide.
Oh, it's right here. Yeah. So conformal means that you can cover things very well. Say I had something like this, a MEM structure. And I wanted to deposit a film on top of this MEM structure. Well, the film is going to be conformal if it can do this. Come down here, go on this edge here, and be the same thickness everywhere. And then even get under this thing. That's a conformal film. That's what I mean by conformality. It conforms to the surface, no matter what the surface is doing. Okay, by uniformity, you're usually talking about a wafer. And this is what I was talking about before, about using the equation versus not using the equation. Sometimes it's futile to use the equation, because if this is your wafer here, and you want to deposit a film on this wafer, the ideal case, of course, is where the film is exactly the same size, thickness throughout that wafer. But what really happens is the film, depending on your deposition, may look like this. Maybe thicker in the center than on the edges, and maybe thicker on the edges than in the center. Okay? And so this is something that's non-uniform here. And that matters a lot, because as we'll see later on, when we're going to etch this film, right, it's much easier to etch if this is uniform. Because now, because I've got parts that are this and parts that are this, I have to make sure I over-etch these parts here. Right? And once I over-etch those parts, then once I've got rid of this film, now I'm etching the film underneath it. And that film better be able to hold up to that etching. And so it complicates a lot of things that your film is not uniform, but this is reality. Your film is going to be non-uniform in basically every process that you put down. Maybe you can argue ALD is more uniform, but sometimes if you use that tool, no, maybe not. Okay, so there's, this is non-uniformity. So, that's a problem with sputtering too. Okay, the substrate can heat up, and that causes non-uniformity across the wafer. So if it heats up, different temperatures in different spots, then you could actually get different deposition rates at different spots. But it's still more uniform than evaporation. Okay, so this is why people like sputtering. So in CMOS, when they're putting metals down, at least for 0.18 micron technologies and that sort, and higher, that's usually a sputter deposition of aluminum. Well, the initial films are aluminum and tungsten, then they have copper higher up. Okay, stress can be controlled by changing parameters in a sputter deposition. So you can change plasma power, that sort of thing, to control the stress of the film. So there's going to be stress in both evaporation and in sputtering. Okay? In sputtering, you can control that stress by changing a lot of your parameters here. And so what's wrong with stress? Here's what stress does to you. And we'll talk about this quite a bit more later on in the class. But say this is your wafer here. And say you've put your film on this wafer. And you were hoping that that film would stay nice on this wafer like this. But what happens in the end, film comes down, then you cool it down, the film starts peeling off. Okay? That's what could happen if you have too much stress in that film. Okay? And so that's the art of MEMS pretty much. Okay? MEMS technologists are different from CMOS technologists because MEMS technologists care about stress. Okay? And it's something we're going to care a lot about later on in this course. We're going to do a lot of analyses to make sure we understand stress and how to predict it, how to get rid of it. Okay? That's why I told you, right, when I started my company, and we were trying to use a CMOS foundry as a foundry, it took a long time for them to learn how to do it. Okay, because they were great at depositing films, very pure films and that sort, but they weren't great at depositing films that didn't curl up after they were released. Okay, and you have to teach someone how to do that. It takes time to understand that. You're going to learn that in this class. Okay, but different types of depositions have different stress. Putting down metals through evaporation and sputtering, that's a lot of stress. But a better way to put down something where you have better control of the stress is through chemical vapor deposition. Okay, so let's talk about that now. So in chemical vapor deposition, you have even better conformity than sputtering. You can form thin films on the surface of the substrate by thermal decomposition and reaction. So this now involves a chemical reaction. Both of those other techniques that I just talked about, evaporation and sputtering, there's no reaction going on. That's physical, right? You're physically depositing that film on the surface of the wafer. In this case, now you're relying on a reaction to do that. So you're depositing the desired material directly from the gas phase. You can perform at pressures for which lambda is small, so you get a very random coverage, so very good step coverage is possible. And this combined with relatively high temperature leads to excellent conformal step coverage. So we just talked about conformality. This is the type of deposition that can get underneath a structure, a suspended structure. Okay? And so what can you deposit with this? Well, all sorts of films. Right? So you can do polysilicon, silicon nitride, silicon germanium, metals, tungsten, molybdenum, tantalum, lots of different things. So this is why this is one of the most popular ways to put down films when you're doing a process. And so here's the CVD process. Very similar to oxidation, but some differences here, right? So you have a substrate, of course, your wafer. You're flowing gas through this. The gas has to make its way to the wafer from the major flow of the gas stream. Okay, so gas species move to the substrate, and then they adsorb to the substrate. They don't necessarily react right at that point. If your temperature is high enough, then the atoms can migrate, okay, to seed areas where you have reactions occurring. So the atoms migrate to those areas there, and it's this migration that gives you conformability. Okay, if the atoms just came to the surface and reacted right there, you would not get conformal coverage. Right? But the fact is you're putting enough energy into this process that the atom can get here and can actually move from here to the bottom there and then react if there was some seeding going on at the bottom. So that's where this step is very important, the atoms migrating here. So it determines the ultimate conformality. And it's energy dependent, which tells you it's temperature dependent. So right here I'm going to tell you something you need to remember. Okay, and that is that the higher the temperature of the CVD process, the more conformal that process is going to be. So you can almost make that decision. Right? If I'm going to deposit polysilicon at 600 degrees C, okay, that's going to be conformal. That's a high temperature. If I'm going to deposit oxide at 400 degrees C, nope, that's not high enough. It's not going to be conformal. Okay, so you can make that decision almost entirely by what temperature you are depositing at, whether it's going to be conformal or not. That's a very important thing that I just said. Okay, so after this migration, you get the reaction. Okay, and here's the reason why there aren't an infinite number of these reactions. Not only do you have to have a reaction that occurs that creates the material that you want to deposit, you better have byproducts, and right, all chemical reactions have byproducts, right? One of them is what you want. The other things maybe not what you want. But those other byproducts better be gaseous, or at least better be removable in some way. And the best way to do that is they're gaseous and can flow out of the gas stream. Okay, so that's another requirement in finding a chemistry that works. So that's why there's not an infinite number of chemistries that work. All of these things have to happen in order for this to work. All right, so this is just what I just said in words, so I won't go through that. I guess I've got some nice pictures of conformal versus non-conformal. Yes?
What are the seeds that you mentioned?
These are areas where the reaction starts occurring. Okay, that's sort of a statistical thing, and it depends on what your surface looks like. So, for example, maybe a defect on the surface or something, and maybe they want to go to that defect, and that's where a lot of things start, right? So there are things that make the activation energy for reactions smaller. Okay?
So it's not something that you physically put there?
You don't have to physically put it. It's going to be there. It's physically there because not all surfaces are perfect, right? All surfaces vary a little bit, and so they're going to have a different activation energy for the reaction to occur, right? And so that's what's happening. You don't want this to react immediately on the surface because then it won't be conformal. Or maybe you do if you don't want a conformal film. Okay, but these are things you have to look into and control. Things you'll learn about in 243, but that's all I'm going to say about it here, actually. Okay, so we can model this whole process as well. It's the same as oxidation modeling. Okay, so I'm going to do this very quickly, right? I can define a concentration gradient, right? Concentration versus distance. Now there's no film to go through because you're just depositing on whatever the surface is, right? So you have some concentration in the gas phase here, some concentration gradient to the surface where the reaction is occurring. I can define a diffusion constant like this as well, just like I did for oxidation. In the end, we can call that a vapor phase mass transfer coefficient. It has to do with diffusion. I have a surface reaction rate as well, exact same equation that I had for oxidation. K sub S, which is some constant times the concentration at the surface. And now just a little bit of math, and you end up with this equation right here for the growth rate. So the growth rate ends up being equal to sort of this parallel combination operator. Everyone know what this is? Everyone know what this is? The EEs will know what that is. Do the MEs know? No, the MEs don't know. So this is when you have parallel resistors, how they... I have it here. Yeah, it's this. It's this equation right here. And so every time I use that operator, I'm just assuming you're taking these and pushing them into that equation. And I will call that parallel operator. Later on, we'll find that I shouldn't be calling it parallel because it's not for springs and dampers. But I'm an electrical engineer, so I'm going to call them parallel. But that's what I mean, that operator. So why do I like to use that operator? Because that operator just basically means the smaller one wins. Okay? So anytime you see something like K sub S in parallel with HG, if K sub S is 10 times smaller, more than 10 times smaller than HG, this is equal to K sub S. Okay? If HG is 10 times smaller than K sub S, this is equal to HG. The smaller one wins, right? Smaller is better for this operator. It's just like MEMS. Okay? And so this is the growth rate here. And so we can look at this and we can sort of define different regimes of growth rates. Right? So we have a case where K sub S is much greater than HG. Right? That means the reaction rate constant is very large. The reaction at the surface is going to take place very fast. So surface reaction rate much larger than mass transfer rate. So naturally, HG is what decides the growth rate. Right? The smaller of the two decides the growth rate. And we just call this the mass transfer limited growth. Because this is now limited not by how fast it reacts to the surface, but how fast it takes for the gas reactants to get from the gas stream to the surface. Okay? On the other side, right, if HG is much greater than KS wins in that equation. So it's KS times this, and it's surface reaction rate limited. Okay? The mass transfer is so fast that the surface reaction can't keep up with it. And so you're depending on how fast that surface reaction occurs in order to figure out how much film you have. All of this has, the surface reaction too is an Arrhenius character. Right? Mass transfer is not necessarily Arrhenius. And so that's how you can tell the difference between different reactions. So you can actually plot curves like this, which is sort of log of growth rate versus temperature. And you could see that at low temperatures, versus 1 over temperature, at low temperatures, which is this far along the axis here, you get an Arrhenius relationship where the slope conforms to the activation energy. But at higher temperatures then, the reaction rate is so fast that now you're limited by how fast the reactants can get to the surface. And so you see this. And so usually you see a knee point here where you can then decide where you want to do your deposition, which you think you have better control of. Oftentimes you have better control of how fast you're shoving gas particles in versus the reaction rate. So oftentimes you like to do high temperature depositions so you can get a little bit better control of how fast that film is growing. Okay? Moving right along, there are many different types of deposition systems. I have them in these notes. You can look at them at your leisure. I'm not going to go through them, except for low pressure chemical vapor deposition, which I think is one of the most important ones. We have a lot of furnaces up in the lab. They're doing LPCVD because this is one of the most convenient ways to do it. The way this furnace looks is usually it's a tube. You have wafers standing in this tube. You could put lots of wafers in this tube, right? 50 to 100 of them at a time you can deposit on. That's why people like this so much. It's many wafers at a time in production. That's fantastic. They're low pressure, so the pressure is usually in the 200 millitorr to 2 torr range. You get all those characteristics for low pressure, so the dep rate is going to be low compared to other types of dep rates, but you get very good control. You do have some maintenance because over time, whatever you're depositing deposits on the walls, and you have to clean the walls of the quartz tubing every now and then. But one of the best ways to deposit films right here, low pressure chemical vapor deposition. You can also do plasma enhanced chemical deposition, chemical vapor deposition. This is maybe number 2 in preference for deposition. What this is doing, right, for this whole process, for these reactions to occur, you need energy. You can supply energy by temperature, but you can also supply energy through a plasma. And so that's all this is doing. This is putting the energy in for reaction through both temperature and the plasma. And why might you want to do this? Well, you may have some process where you've put a film on the process that cannot stand up to a higher temperature. And so instead of doing a high temperature LPCVD deposition, you do a plasma enhanced LPCVD or CVD deposition so that you can do it at a low temperature. So it doesn't affect the films that are already on the wafer. This is a problem you will see time and time again in MEMS. So in MEMS, a lot of people would want to use plasma enhanced chemical vapor deposition, PECVD. But the problem with PECVD, it's not as good a film as LPCVD. Okay, so pinholes can form. right? Why do pinholes form? Well, in LPCVD, right, remember the way that that works is you have to have an activation, right? You have the add atoms coming on the surface and they move around and they get to some point where the activation energy is low enough and they react. Okay, well, in an LPCVD furnace, the temperature is uniform, right? In a PECVD type situation, you're at high temperature, but the rest of the energy is coming from the plasma, and maybe that plasma isn't getting to some spots, right? And so that means you don't have the energy going to those spots, which means you have a point where there's no reaction. You've got film everywhere except for that little pinhole there. It could be a minute pinhole. It could be like 10 nanometers wide or so. But that 10 nanometer wide pinhole could kill you, right? Especially if that film was supposed to block an etchant that's coming afterwards from reaching the film underneath it. Okay, so pinholes are bad news. And in MEMS especially, they're bad news. And that's why people shy away from PECVD for MEMS. This is one of the reasons. You can solve this by putting a very thick layer of PECVD down. But there's a problem with that too, and that's stress. Okay, the thicker that layer, the more stress problems you have. Now there are ways in PECVD where you can actually control stress by changing powers as you deposit. Deposit at high power, low power, high power, low power. So you're getting different stresses that are acting against each other. But I wouldn't try that at a university. In production, maybe you can do that. Maybe you can do it. But at a university, it may work once. But the next time you try it, you got to redesign the whole thing. Because the equipment in the university are just not dialed in. Right? You got all sorts of people using the same piece of equipment. Every time you use a piece of equipment in the university, you always need to dial it in yourself. Okay, that goes to etchers. I'll give you a piece of advice here. Never trust an etcher, period, if you're doing processing in a nano lab at any university. Right? Even if the person before you was conscientious enough to put down his or her etch rate, do not trust that number. Okay, because there's all sorts of different things that decide on etch rates. Now, always determine your etch rate yourself with a dummy. Okay, that's just an aside right there. And never process more than one wafer at a time. Okay, you could do it in industry, that's the way it's supposed to work, but in research, do not do it. Okay, you will lose that wafer at some point in the process. Let's see, other problems with PECVD, non-stoichiometric films, incorporation of other things into the films. Okay, so that's PECVD. So now let's start marching through different recipes for deposition. And I'm truly going to march through this because you have these in your notes here. But for polysilicon, usually this is decomposition of silane. Okay, this is silane, SiH4. And what you're doing is you're exposing that to a high temperature, like 600 degrees C as an average. And it decomposes in the silicon and hydrogen. And the hydrogen is swept away through the pump system here. This is a 600 degrees C temperature. 600 degrees is high enough to get a conformal deposition. That's the high enough temperature that the add atoms can really move around. And polysilicon is one of those depositions where if you have an underside to something, you can coat the underside with a polysilicon deposition. Okay, you can deposit polysilicon either undoped or you can do it in situ doped. Okay, to in situ dope, well, what do I mean by doping? Does everyone know what doping is? Emmys, you know what doping is? Okay, good. So doping basically means you're making the silicon conductive by putting impurities into it. And so phosphorus and arsenic are types of impurities that you could put in there. So you can add phosphine, and actually our tubes in the nano lab can do phosphine doping. Okay, so you could do in situ dope with phosphorus. Okay, that, however, greatly reduces the dep rate. So if you're going to do it and you want a MEMS film of 2 microns thick, be prepared for a 12-hour deposition. Okay, it's convenient, right? You go in, you go to sleep, and you come back. Right? But if you want 2 microns, it's going to take a long time if you want an in situ doping. The other thing you could do is make it p-type instead. Add diborane gas. That actually increases the dep rate. Okay, we don't have this in our lab. Why don't we have this in our lab? Diborane is pretty nasty stuff. Very toxic. Okay, just a few ppb of that stuff can kill. Okay, so in a university fab, forget it. Right? No diborane. Phosphine is, I mean, there's nothing safe in the labs, right? Phosphine is not nice either, but it's not diborane. Okay, so you got to be careful at every step in the lab. That's why we have those rules in this lab. It's dangerous, right? But if you follow the rules, right, there are no incidents. And there haven't been any incidents in the lab that have been, horrendous or so, because we have these rules, right? You spend a lot of time qualifying an equipment. It's a process that takes a long time, and it's going to piss you off, but there's reasons for that, and that's safety. All right, so silicon dioxide CVD. So there's a couple, I'm using every second we have here. So silicon dioxide deposition, so there's a couple cases here. So one, are you going to do your silicon dioxide deposition after metallization or before metallization? Okay, this is one of those instances that you have to worry about in process design. Right, if you have a metal already on your wafer and you want to put a film down, you have to be careful about temperature. Okay, why is that? Well, aluminum will melt at a certain temperature, but you're more worried with aluminum about a silicon aluminum eutectic point. Right, that's where it'll react with silicon to create a eutectic material, and that happens at 577. Okay, at even smaller temperatures, even less than 500 degrees C, aluminum will grow hillocks. These are little bubbles like blistering on the aluminum. You can't take that in a CMOS process. Okay, similar issues for copper metallization. So one way to deposit oxide over aluminum is to do a low temperature oxidation. So that's what's called LTO. So when you see the word LTO, that means low temperature oxide. It's using this reaction, silane and oxygen, at about 400 degrees C is what it is. Because that temperature is very low, what do you expect? It's not going to be conformal. This is not a conformal deposition. You can add phosphine to it as well to create phosphosilicate glass where it's doped with phosphorus. Why would you want to dope oxide with phosphorus? Well, if you dope the oxide with phosphorus, you can reflow it by putting it at high temperature. So say you've deposited a film, and it's on topography, and it's sort of following that topography, not following well because it's not conformal. If you want to flatten it, you can reflow it by taking it to high temperature, and it flows like water. Not quite like water, right? Like molasses or something, very slowly, like glue, right? So you get a flatter surface. And so that's why you may want to use PSG. In MEMS, you also might want to use it to auto-dope other films. And we'll talk about that in the next lecture. We should finish up now. So we'll continue this on Tuesday. We're done.